Okay, let me start. Hello everyone, my name is Akari Asai, and today I will talk about recent papers and building language model augmented by retrieval component to make it more factual and also improve the generations. Okay. So language model has shown to be quite effective and capable on many diverse NLP tasks. And this is an infographics from Pound paper, which is one of the biggest model from Google. And as you can see, as we scale up the model size, model can do not only just language understanding tasks, but also do many diverse tasks, including translation, summarization, or more complex reasoning tasks. Those success of large language models are not only just on academic benchmark, but also on like more real-world diverse user interaction. For example, now we can ask ChatGPT to do many different things. For example, I can ask ChatGPT to suggest Japanese recipe using some ingredients at home, or I can also prompt ChatGPT to answer questions from homework assignment of undergrad artificial intelligence course. Despite the impressive capability across many different tasks, many people also notice that those language model output can include a lot of factual errors, or what people call hallucinations. So for example, if I ask ChatGPT explain Akari Asai, including her famous papers, the first paragraph of ChatGPT mentions that I am an NLP researcher, which is correct. But ChatGPT also listed 3 papers. All of those papers are not actually like my paper. The first one is a paper from OpenAI a while ago with many citations. And second paper is a paper about water metering in material science, which also has a bunch of citation published at Nature, but it's not my paper either. And the last one is another famous survey paper, but again, like it's not my own paper. As you can see, ChatGPT or those really capable language model output look so convincing, plausible, and it is really difficult to find which statement is incorrect, which statement is correct, without knowing the subject or having access to information. Those factual errors can cause a big catastrophic errors in real-world use cases. For example, some lawyers got fined because they submitted hallucinated or like factually incorrect legal cases, because the lawyers believe that ChatGPT generate something that actually exists. Or someone started a lawsuit against OpenAI because the person found that OpenAI is generating false or misleading claim about him. Those errors are not only about ChatGPT, but also any other like large and competitive language models. Last year, Meta released a scientific language model, Galactica, to help scientists write paper or conduct literature reviews. But many scientists noticed that this model can generate a lot of misleading or factually incorrect information about science. So Meta had to take down the demo a few days after its first release. So now we know that those language models can generate a lot of factual errors, and it can cause a big problems in real-world use cases. But why we cannot solve these issues, despite that we know that this issue exists for a while? Because this is inherently from the pre-training itself and how we use the model in practice right now. So right now, we pre-train language model using a really large scale pre-training corpus, which can include like 1 trillion tokens. We train language model using next token prediction task on these massive text data. And so during pre-training time, the model, given the text, for example, Barack Obama is, and then like the model is learned to increase the probability of the next token American during pre-training time. But inference time, we don't have any explicit access to this data sources. So we assume that language model can memorize or internalize those factual knowledge from pre-training. And so once we prompt language model with, for example, like prompt like who is Barack Obama, then the model can generate correct output using the information presented in pre-training corpus. But this is difficult because even human cannot memorize everything in the world. And if I ask question like who is Akari Asai, then language models are likely to hallucinate because my information may not be that presented that much in pre-training corpus. Or even if we ask about factual knowledge that is widely discussed, for example, who is a prime minister of Japan, then the ChatGPT, GPT-4, GPT-3 outputs are all incorrect because this person stepped down in 2021. But as we train ChatGPT or like those large language models on the pre-training corpus, which is collected a while ago, for example, like in 2021, the knowledge is still fixed to the like point of like 2021. So those models may generate factually incorrect information that used to be true, but not true anymore. These are the examples of why we shouldn't try to memorize everything in language model parameters because of those like layer entity issues or those like temporal dependencies. And also if we try to memorize everything, we typically need to increase the model size to like billions or trillions of parameters to increase the capacity of the model. My research is focusing on retrieval-augmented language model, which instead of just depending on language model parameters, we try to augment language model with retrievable knowledge at inference time so that we can avoid those issues related to parametric memorizations. So how it works is, given the input query, we use a retrieval system to find useful information in large-scale external knowledge. Here we can find information about my art, about Akari Asai, or like about Japanese Prime Minister right now. And retrieval system returns those top documents to language models, and language models try to incorporate such external information at inference time so that they can avoid those issues like hallucinations. And we recently had a tutorial at ACL 2023. And if you are interested in this area, please go look at our website. Those retrieval-augmented language models are now used in many real-world applications, including language model-based search system, for example, U.com, Bing Chat, or Perplexity. And also there are many libraries with like thousands of users to develop retrieval-augmented language model for different end goals. Despite the popularity of retrieval-augmented language model, there are still many major open questions. For example, when we deploy language model-based system, usually like user asks so many diverse questions that are not and many of the questions may not always requiring knowledge retrieval. So one question is, do we actually need to do retrieval every time for every sequence, even though like the user's queries may not require any retrieval? For example, if the query is just about write an essay about your best summer vacation something, then we don't need to retrieve at all. Another question is, in common framework, and also those unnecessary retrieval can increase the cost of inference. So if possible, we want to avoid for like efficiency, and also later I will discuss the issue of those unnecessary retrieval. Another question is that in those retrieval-augmented language model framework, we typically retrieve, but we just input retrievable documents in input space. And there's no guarantee that those information is actually used by language model, or like we don't have any control on how language model uses those informations. So my research is trying to understand how it works, and also like how to improve them to make it more reliable and controllable. Today, I will talk about two of our recent papers. The first one is trying to understand the limitation of language model and also like retrieval-augmented language model to build a better system, a better and more reliable system. Second, I will talk about a recent archive paper, which conduct instruction tuning of retrieval-augmented language model to make it more widely applicable and also reliable. And I will conclude this talk with the summary of those two papers and also some new interesting frontiers. And so for the first paper, this is a paper with my amazing collaborator at UW, AIQ, Johns Hopkins, and published at ACL. This is not a method paper. This is more about like analysis paper to understand the limitation and effectiveness of language model memorization and retrieval-augmented language model. The question we had in this paper is to when language models are likely to hallucinate and how to fix these issues. When we prompt language model who is Barack Obama, then many of the like state-of-the-art language model can answer correctly. Well, if we prompt language model who is Cassie Saltzman, who is another US politician, then many language models can generate incorrect output. But at least like when we started working on this project, we didn't have any good understanding on when language models output are incorrect, when their outputs are more reliable. And also, if the current language models fail to answer correctly, what are the best approaches to fix those issues? We want to fix these errors so that the language model can output more reliable generations, even for the cases where the current models fail to output. So for example, one approach is just scaling up language model and hoping that scaling scales solve those issues. But another approach is incorporate retrieval augmentation or doing retrieval to enhance the input space, and then hoping that the language model can fix those issues at inference time. In this work, we first conduct analysis on what kind of factors affect language model memorization. And we found that language models struggle to memorize long-tail factual knowledge, which is likely to be less represented in pre-training time. And we found that those cases cannot be solved by just scaling up the model size. So in the second part, we tried to see how effective retrieval augmentation is in those long-tail cases. And we found that for long-tail retrieval augmentation is quite helpful, but for more common cases, for example, like queries about Barack Obama, then retrieval may not be really helpful or even harmful. So the last part of this paper, we tried to understand if we tried to explore whether it's possible to adaptively incorporate this retrieval component and also language model component to improve the performance and also efficiency. This area of memorization is still new, but there are like many exciting papers. For example, one of the most famous paper is memorization of training data, and their finding is that if the training data or like subsequences in training data appears more frequently, then the model memorize more. And also scaling up model size makes the model memorize more. And a similar finding was reported by another paper about arithmetic reasoning. For example, if a number appears more frequently than other numbers, then the number may be memorized better than the model. Concurrent to our work, there's a paper that tried to understand the effect of those frequency in pre-training data and the model's memorization of factual knowledge. And the finding is similar to other two papers. So if the entity names, person name or location names appear multiple times in pre-training time, then the model memorizes more. And if we scale the model size, the model can memorize more and more factual knowledge, so it can answer correctly in like downstream tasks like question answering. So the core finding of those papers is scaling up language models, improve memorization, or eventually like solve the hallucinations. We conduct an evaluation analysis and evaluation from slightly different perspective. And actually we have different findings from those papers, which I will discuss later. In this paper, we focus on factual knowledge, what can be represented as a knowledge triple format: subject, entity, relationship type, and object. This is quite a common format of knowledge in NLP. And we formulate the task as open domain QA, where we ask a natural language question. The model is expected to predict the final answer. In this work, we focused on two dimensions of analysis. The first one is subject entity popularity. And this is based on our hypothesis that a question or like factual knowledge about more popular entity can be memorized better than the model, better than the fact about less popular entity. For example, the knowledge about Barack Obama might be memorized better than like the knowledge about Cassie Saltzman. And we evaluate this popularity based on the Wikipedia page view. There are some prior works try to evaluate, try to use frequency in pre-training data. And we found that popularity can be a good proxy of frequency of pre-training data, frequency of substring in pre-training data. But one bottleneck of this analysis based on frequency is in many language models such as ChatGPT, we don't have access to pre-training corpus. So we assume that this popularity can be a good proxy across different language models. Another aspect is relationship type, fine-grained relationship type, because we believe that even about the same target entities, Barack Obama, some question or some factual knowledge about specific aspect might be memorized less than other aspect. For example, it's easy to answer his occupation, but it might be harder to answer like which elementary school he went to, something like that. To conduct this fine-grained analysis, we construct a new dataset to get fine-grained annotation of relationship type and also the diverse distribution of popularity. How it works is that we first randomly sample many knowledge tables from Wikidata, which is one of the biggest knowledge graph in the world right now. And we sample 15 different relationship types. Then we convert those knowledge tables into natural language format based on the predefined templates. By doing that, we can cover many questions that are many questions with diverse popularity distribution. Here's a popularity distribution of 3 different question answering dataset: natural questions, entity question, and pop QA. Natural question is one of the most widely used question answering dataset and used in prior analysis. But the issue is that natural questions are highly biased towards more popular fact because it's based on Google search queries. There's another dataset called entity question that is generated by sampling knowledge people from Wikidata, which is similar to our work. But this dataset is highly biased towards the rare entities. And in this work, this pop QA, we enable to control popularity distribution. So we try to cover those diverse, popular, and long tail fact to provide more comprehensive analysis. Now I would like to talk about some key findings from our first analysis about language model memorization. The key finding is that across different language model, different size, different language model family, we see a strong positive correlation between the model accuracy and also popularity. And higher correlation happens in larger models such as GPT-Neo 20 billion or GPT DaVinci 003. And we believe that this is because those models have more capacity to memorize. And this memorization trends happen across different types, not only just single relationship type, but these trends are even more stronger in the relationship types require fine-grained knowledge memorization, such as the director of movie or author of the book, something like that. So those findings may suggest us the scaling up model size enables the model to memorize more. So if we increase the model size to almost infinite size, then maybe we will eventually solve hallucinations. But we assume that this is not true based on our analysis, based on our per popularity analysis. So here I plot model performance across different popularity range, and the red line shows the model performance of more popular fact or question about more popular entities. And as you can see, for this red line shows that as we scale up the model size, we can clearly see the upward trajectory of this question answering performance. But for the long tail fact, which is represented as blue or green line here, we don't see that much performance improvement or almost flat trend, even if we scale the model size from 1.3 billion to 175 billion. So our takeaway from this analysis is that scaling may be helpful for memorization of more popular factual knowledge, but it may not be helpful for long tail. And this has a great implication for real-world use cases. In real-world use cases, such as, especially in expert domain like legal, science, or code generation, some code generation, those target domains can be considered as long tail because they may be discussed much less on the web compared to normal factual knowledge or popular factual knowledge like entertainment. So in that case, even if we skip the model size, we might still see how issues like hallucinations in those expert domain or safety critical domains. So in the second part of this paper, we try to see whether retrieval or retrieval augmentation can help us to overcome the issues of hallucination in long tail. Here we tried a really simple framework, Retrieval-Augmented Generations, which retrieve helpful Wikipedia articles to any query, and then we augment the input prompt with retrieved document. And by doing that, we hope that language model can update incorrect predictions by using this information presented in the article. So this few simple approach, without requiring any training change or architecture change, can significantly improve performance across different models, families, and scales. As you can see, there's a huge performance improvement from blue bar to red bar, especially like a bigger gain in smaller language models. And one notable finding is that retrieval-augmented 1.3 billion model can even match GPT-3 175 billion model, which indicates that retrieval-augmented language model can be much more parameter efficient than the non-retrieval-augmented models. So this is great, but what we wanted to understand is why retrieval is that effective. What we found is that retrieval augmentation can be super effective in long tail, while language model can struggle. So in this case, here I show the model performance with and without retrieval, and retrieval augmented language models are indicated as the dashed line, red and green dashed line. As you can see, those retrieval augmented language models are much better than the vanilla language model, which is represented as blue line here. Well, interesting finding is that retrieval augmentations may not be that helpful in the questions on the question about more popular entities. Here, the orange or like green line shows the model performance without any external retrieval. And as you can see, those two straight lines are almost like better than the retrieval augmented language model in those areas. The reason is that sometimes retrieval can be harmful, especially like when retrieval model failed to retrieve helpful document. So here I show the retrieval performance of two different question categories. The first category indicates the model performance where the retrieval performance where the language model only baseline failed to answer, while retrieval augmented baseline can answer correctly. And as you can see for this part, the retrieval accuracy is 83%, while for the questions where language model without any retrieval can answer correctly, while retrieval augmented one failed to answer correctly, then the retrieval performance is 14%, which means that sometimes retrieval model can return unhelpful or like irrelevant documents, and it can confuse a language model which counterfactually can answer correctly or like already knows answer. And based on this finding, we were wondering if it's possible to adaptively combining those two components, language model and retrieval model, to enhance the performance and also reduce the inference time cost of retrieval augmented generation. What we did is quite simple. We just set the threshold about popularity, and we use retrieval only when the popularity of the subject entity is lower than this. While like otherwise, we just use a standard language model. This really simple approach can actually enhance the performance a lot, especially on like much bigger and competitive language model. So here, the red bar shows the model performance with retrieval, always retrieval baseline, and the orange line shows the model performance with adaptive retrieval. And as you can see, there is a big performance improvement from always retrieve and adaptive retrieval in GPT-3. And I also wanted to highlight that we conduct how much retrieval reduction happens across different models. And we found that as we scale the model size, the model can skip retrieval more often than the smaller model. In case of ChatGPT, in case of GPT-3, O2 or O3, then the model can skip retrieval like 40% of the time. This means that adaptive retrieval can be more cost efficient because we can reduce the numbers of retrieval, and also like we can reduce the context length of input, context length of language model input. And so we found that this adaptive retrieval can reduce the latency per query at inference time, or can reduce the API cost for GPT OpenAI APIs. The summary of paper is that language model can memorize a lot, but their memorizations is highly affected by the popularity of frequency of specific factual knowledge or like language model scales. And even scale up the model size may not be really helpful for long tail factual knowledge. And in these cases, non-parametric or like knowledge retrieval can be super helpful, but those retrieval-based approach can be harmful if the language model already memorized the factual knowledge and language and retrieval component fail to find the relevant document. So we tried a really simple approach to combine both two components and found that this is more effective and also efficient. But I have to note that the third part, the adaptive approach, is super depending on heuristics, and it only works for simple factoid knowledge. This kind of inspires us, or like makes us wonder, is it possible to develop more general purpose, generally applicable adaptive retrieval-augmented language model method, so the language model method. And also we were wondering if it's possible to make language model itself to predict whether it should retrieve or not, given diverse input. So that's result in our second paper's flag, which tries to train a language model learn to retrieve, generate, and criticize its own output and also retrieve document to make it more reliable and controllable. This is a joint work with my collaborator at UW, AI2, and IBM. Before talking about our framework, I would like to briefly discuss how the standard retrieval-augmented generation works. Typically, in standard approach, given the prompt, we always retrieve fixed number of documents, for example, like 3 documents here. And given those retrieved documents, we simply insert these retrieved documents before or after original query or prompt, and hoping that like language model can figure out which one is helpful and like how to use them. This retrieval augmentation can be super effective for the task like open domain QA, but when it comes to more open-ended long-form generation, there are some major issues that should be addressed. First of all, as we briefly discussed in the first section, the current language model may not be that robust to unhelpful or like irrelevant context. This is because those language models are not trained to use external or retrieved document. Here, the second document doesn't talk about how the US states get their own names, and it just talk about like what kind of like baby names are popular in Texas. But the current language model may not be trained to ignore those unhelpful contexts, so this unhelpful document may implicitly or explicitly affect the model output. And this sentence indeed include hallucination. The second case is that even though the retrieved document is helpful, there's no guarantee that language model output is fully supported by the citation. For example, here, the third paragraph is helpful, but the resulting model generation can add some additional information that is not discussed in the original document. Here, the original document only say California was named after a fictional island, but somehow language model ignored this knowledge and insert some hallucinations. This is because language model can still just ignore and like depend on its parametric memories. Last thing is, especially when we deploy such language model-based system for more like real-world use cases, not always the user's query require such retrieval. For example, if many people use ChatGPT for more open-ended, non-knowledge-intensive tasks, for example, like write an essay about your best summer vacation. And in that case, we are unlikely to get some useful information from Wikipedia, but the current retrieval-augmented generation always retrieve fixed number of documents. So like it can retrieve some like definition of summer vacation or like definition of vacation from Wikipedia, and then like it input those unhelpful documents in input space of language model. So this is not efficient because this is really unnecessary, and we have to still like do retrieval and retrieval augmentation. But it can also confuse language model and makes the language model output worse, as we discussed in problem 1 and 2. And there's some related work or like concurrent or recent work in the area of retrieval augmented generation. And for example, Atlas is pretty popular paper last year, which pre-trained retrieval augmented language model a bunch of unlabeled text and then conduct future task-specific fine-tuning to make it learn how to use those information for specific downstream tasks. And in this framework, they always retrieve top 100 and use top 100 documents, and hoping that language models learn to find relevant documents and learn to how to use the document. More recent follow-up is from Matter, which instruction tune retrieval-augmented language model so that we can adapt those models for new downstream tasks without fine-tuning. But this model still conduct the always retrieval strategy, retrieving fixed number of documents, and they try to aggregate the output from multiple different paragraphs, but depending on retrieval score. There's another concurrent work which tries to use natural language inference component, which evaluate whether this document is helpful or not as a part of the retrieval-augmented generation pipeline. This one still almost always retrieved, and also depending on task-specific classification model that needed to be fine-tuned for each downstream task. Lastly, there's a paper called ToolFormer, which makes the language model learn to insert API code during generation. This enables kind of like adaptive code or like adaptive or iterative code of retrieval model. So it's similar to our work in that sense. But in this work, there's no way to give feedback on like whether this retrieved document or answer is helpful. And also because of their the way they conduct pre-training, the API code is limited to named entities. Based on those issues and limitation of prior work, we introduced a new approaches called self-reflective retrieval-augmented generation, in short self-RAG. In this framework, instead of always retrieve documents for every single query, we make language model to figure out when it should retrieve external knowledge. So for example, given the query, how did US states get their names? We first prompt language model, and then language model may start generating sentences, because for the first sentence, language models already know that US states got their names from a variety of sources, but it doesn't require really fine-grained knowledge, knowledge retrieval. I'm sorry. Let me turn off the Slack notification now. Sorry. In this case, but when it comes to the second sentence generation, the model needed to retrieve external knowledge to generate factually correct sentences. So the model generates a token, special token, which trigger retrieval component. And given the special token, we use the retrieval component to find helpful documents. Given those multiple retrieved documents, we process those multiple documents in parallel using batch decoding. And so we will have like multiple possible like continuation given different condition on different paragraph. So for the first paragraph, the document is talking about 11 states get their names from the person. So the model outputs the relevant token, then the model starts generating the output given this token. Well, for the second document, it just say like popular baby names. One of the popular baby names is Emma. So it's not really helpful. So it generates a special token indicating that this sentence, this retrieved document is not really helpful. And the third paragraph is actually helpful. So the model generates relevant token, then it starts generating the output. After this generation, we also make the model to criticize its own output. And based on those critique, we select the best segment. So for the first one, the model generation is fully supported by the evidence. So the model generates the fully supported token. While for the third one, the document only says that California get their name from a fictional island, but it doesn't say any like specific title. So this sentence is indeed factually correct, but it's not fully supported by the evidence. And based on those reflection tokens, we rank the generation at each time step and select the best one. This self-RAG also enables us to completely skip retrieval if it's not necessary. For example, in this case, the query doesn't require any factual grounding. So our model generates no retrieval token for like after each segment and completely skip retrieval, and only like gives a final feedback on the overall quality. Then how it works? We train this self-RAG model by expanding the original vocabulary and makes the model to run to predict output and also this expanded vocabulary, word from expanded vocabulary. In normal language model, we typically have a fixed size of vocabulary, and then the model predicts probability of each subword token given different prompt. So here, given the sentence, US states got their names from a variety of sources, the model may put the highest probability to, like, for example, and we will pick this subword as a continuation. Well, instead of the case, we expanded this vocabulary with deflection tokens with special tokens, which we call deflection tokens. So these special tokens can be the tokens that control retrieval, or the tokens that can criticize the model on output or the retrieved document. So the first two special tokens, the relevant or irrelevant tokens, indicate whether the document is helpful or not. And the second one, supported, no support, indicate whether the model output is supported by the document. And the last one gives the feedback on the overall quality of generation. So given the original prompt, our state of flag model predict whether it needs retrieval or not, and gives the highest probability to retrieve token. And once the model retrieve, then we have retrieved document. And given the retrieved document, the model predict whether this document is actually helpful or not. And in this case, the document is helpful. So the model puts the highest probability to this green token. Once the model generate continuation, then the model learns to give feedback on its own generation, like whether the document, if the generation is supported by the document or not, or like overall quality of generation. In this case, the generated sentence, 11 of 50 state names come from persons, completely supported by the original document. So the model puts the highest probability to the supported token. The key challenge is how to train this set of framework to make a language model to learn to generate reliable and appropriate reflection tokens. In this work, we didn't train retrieval model. So we use off-the-shelf retrieval model, and any like existing state-of-the-art retrieval model can be integrated in this framework. And we trained the generator language model so that it can output tokens from normal vocabulary and also the reflection tokens. To make the model learn to predict appropriate reflection tokens, we use additional language model, critic language model at training time only, which teaches the correct reflection token, which teaches the generator language model to generate correct reflection tokens. This critic model formally takes the input instruction, input X, the document D, and output Y, and it generates the correct reflection tokens. For example, in this case, we have to predict if the output Y is supported by the document D, and the answer should be supported because this Y is fully supported by D. Also, like we can use state-of-the-art language model API, for example, GPT-4 or ChatGPT. This can be quite expensive because in our work, we have to insert multiple reflection tokens, 4 different type of reflection tokens for each sentence or segment. So if we want to create training data with 150,000 instruction following data, then it can be millions of API calls. So in this work, we train critic language model on the data generated by GPT-4 using standard language modeling objective. So given the input X instruction, X, D, and Y, the model learns to predict the reflection token R. After we train this critic model, we augment the original training data from diverse instruction following pairs using this critic model and also the retrieval model. For the first case, this like write an essay of your best summer vacation, we don't need to retrieve at all. So our critic language model insert no retrieval token before each segment and only gives an overall quality token at the end. Well, for the second cases, how did US states get their names? Then we needed to retrieve. So our critic model insert retrieve token, and then we retrieve documents for each segment because each segment with those retrieve token, and then we embed this retrieved document. For each retrieved document, we also run critic model to make judgment on whether retrieved document is actually helpful or like final model generation is supported by this retrieved document. After we create those many instruction tuning data with augmented special tokens, we train generative language model on this augmented training data. So now the training is really simple. Given the input X and also possibly like retrieved document, the generative language model learns to predict output Y from the original normal vocabulary and also reflection token if necessary. And we use the standard next token objective with expanded vocabulary. So it's really just like simple language model training, and we don't need to modify training code, and we can just like use new language models such as like Mr. 6B or like 13B using our training data. At inference time, we leverage these special tokens to improve model generation or like customize model behavior. So again, we process multiple documents in parallel doing batch decoding. And for each paragraph, we generate some reflection token or the critique token about the quality of retrieval or quality of generation. Given this we use those special tokens probability as a feedback or like score from each fine-grained aspect, and we aggregate the score using some weight by taking weighted sum of those ideal reflection tokens. So here, the first paragraph has the highest probability, highest score for the paragraph quality, and also the final generation is fully supported. So we got like highest score. Well, like for the middle cases, for the middle case, the retrieved document itself is not really helpful. So we got really low score. But for the last case, the prompt plus the third paragraph, we get high score for the aspect whether the document is helpful or not. But we got lower score for the final aspect if the document, if the generation is fully supported by the document. And based on this score, we conduct segment level beam search to find top case segment at each time step. So in this case, if we have beam size with 2, then like we keep the top 2 segment at this point. So we keep the generation based on paragraph 1 and paragraph 3, and then we continue generation and conduct segment level beam search at each time step. This also enables us to control models' behavior at inference time. So what we have to do is just need to change the weight parameter for this function f. And so if we want to put more emphasis on whether the model generation is fully supported by the evidence, then we can increase the weight time for like this is supported token. Well, if we put more emphasis on if the model generation itself is overall helpful or like useful, then we can put more emphasis on like is useful a token. This enables us to tailor models behavior towards different type of preferences or like different type of user preferences, which is quite important, but it's hard in like the framework like PPO, fine-grained PPO right now. We conduct evaluation on diverse tasks, 6 diverse tasks, including closed set tasks, classification on multiple choice, or free form generation, requiring a short form generation or long form generation. And for long form generation, we use multiple different metrics to holistically evaluate the model's generation quality. For example, fluency, citation accuracy, correctness, or factuality. During our training, we use 150,000 instruction following datasets from many different instruction following data, and we augment those original datasets using a critic model and retrieval model. And our base model is Llama 2 7B and 13 billion, but again, it's super easy to train new, better model on the top of our framework. And we use 4800 and like takes like less than 24 hours, so it's not that expensive training. As a result, we get much better numbers than existing non-retrieval baseline, including a ChatGPT or like Llama 2 13 billion, and like short form generation. And we also outperform the language model, state-of-the-art language model plus standard retrieval-augmented generation framework, like most of the tasks. Our model also shows strong performance on long-form generation. For example, our model outperforms other models with and without retrieval. Our fact score or like long-form question answering task in terms of fluency or like final model accuracy based on bridge score. I would like to highlight that our model also provide much better citation precisions in those long-form generation. So citation precision evaluate whether the model output is fully supported by its evidence or not. And we use the data set called ASQA, AOCE ASQA, which evaluates the model's citation precision and recall. And in the original paper written by Gao et al. 2023, they found that existing open source model shows much lower citation precision compared to ChatGPT. In an experiment shows that a model indicated as purple line even outperform ChatGPT and significantly outperform all of other open source models. I also want to highlight that by using this self-reflection token, our model can be customized at inference time by simply changing the weight parameters. So here the x-axis indicates the weight parameter for the supported aspect, which indicate if we make this weight term larger, then the model put more emphasis on whether the model generation is supported by the document or not. And as you can see, if we scale up when we scale up the weight term, the model output is more and more fully supported, but at the same time, the model generation quality, the model fluency, overall fluency can be decreased, as you can see on the right side. This indicates that self-reflection can enable us to change the model's behavior by simply changing hyperparameters without requiring any additional training. So in summary, self-RAG enables a language model to learn to retrieve, generate, and criticize its own output, and we conduct instruction tuning language model using a bunch of diverse data with those reflection tokens. And the models are available on like Hugging Face, and we open source a code base. And we show that this model outperforms other language model with and without retrieval in 6 tasks. And also it significantly improves citation accuracies. So now I would like to briefly conclude my talk with summary of those papers and also some interesting future directions, which I'm really interested in exploring. So for the first part, I discussed our recent paper about analyzing the factuality of language model, or like the limitation effectiveness of language models or retrieval-augmented language model. And we found that retrieval helps in long tail, while like scaling language models may not be helpful for long tail. And we also found that augmenting language model with self-reflective or like augmenting language model with adaptive retrieval is the best in terms of performance and also efficiency. For the second part, we introduced new approach called self-RAG, which makes the language model learn to decide when to retrieve, and also like give feedback on its own generation and also retrieve document to make language models more reliable and also widely applicable to diverse instruction following use cases, not only just question answering. But one limitation across those two papers is that we use English Wikipedia as language source, and we only evaluate the model on the task where we can solve based on English Wikipedia information. So it's mostly like about language intensive tasks, but about the more like common language, for example, like entertainment or like basic language of science. But on the web, we have a bunch of diverse information that can be about like many different domains or like represented in many different languages or modality. For example, like Wikipedia is one of the biggest like encyclopedic websites, but there are like many different language sources, for example, like academic papers or code or proof, or like if we want to build language model, which can be useful for like legal cases, then like we needed to use those like legal cases written in like different language, kind of like almost different languages. But right now, many retrieval-augmented generation framework only evaluated and use like those encyclopedic Wikipedia-like website, and it's an open question on whether those model can perform well in completely new domain or like more expert domains. Also, many web documents can be represented in many different languages, and we have like a lot of different language represented in many different formats. For example, like language graph, video, audio, images. I think one of the most exciting directions in this area, retrieval-augmented language model, is trying to implement the reliable retrieval-augmented language model for such long tail and high stake domains. Those expert domains are like long tail essentially, and also like it requires frequent knowledge update. And many of the cases we needed to provide attributions or citations. And it is not possible for like standard language model. Well, it's basically by default completely doable for the retrieval-augmented language model. But at the same time, as we, even in like the non-retrieval language model, those areas are still underexplored. So it's still open question whether our retrieval system can perform well in those domains, or like our language model by default can effectively incorporate retrieval document to generate meaningful output, or like we don't have enough instruction tuning data for those domains. So I think there are many interesting research questions in this area. And also many web documents are represented in some like major languages, but there are like many speakers that uses many different languages, and there's huge inconsistency between like actual number of first language speakers and like the percentage of website represented in like some languages. And most of the web documents are represented English. So I've been working on cross-lingual information retrieval and generation previously in my PhD. And I think now it's even more important to build cross-lingual retrieval-augmented language model to help many people to access information they need and overcome the biases, language model biases towards cross-lingual knowledge. Lastly, many recent papers try to use retrieval-augmented approaches for many different use cases. For example, retrieving images to improve text-to-image generation, or like video, or even like domains like molecule generation. And I believe that there are like many exciting new modalities and opportunities to explore in the future. So this is a wrap up my talk, and thanks for listening. If you're interested in, these are the title of the papers I highlighted today. And if you have any questions, feel free to send email or ask during QA or like one-on-one meeting. And if you have any like feedback, you can submit from Google Form.
Right. Yeah. Yeah, thank you so much, Akari, for this interesting talk. I think like this opens up a lot of new directions. I'm sure like there are a bunch of questions and we have about this, I think. So if there are any questions, I think you should just be able to ask me. Yeah, can you speak?
Hello, thank you so much for this great talk. I had a question about this adaptive retrieval part. How do you figure out that the language model already knows the answer when there's retrieval? And what is the criteria, or what method you use without actually checking if?
So in this case, we explore like many different ways, but we finally decided to do more like Redux definition. So like whether this specific segment requires factual grounding or not, or like we basically prompt GPT-4 to predict whether we can improve this, we can improve the continuation or generation by retrieving external knowledge or something. After we collect training data from GPT-4, we train the critic model based on this data. And we hope that like by doing that, critic model knows like when we should use, or like we should call retrieval system. But yeah, by definition, it's not like precisely like we can adjust this adaptive retrieval feature for based on like whether this specific model A knows this answer or not. So that's one follow-up we can explore.
Thanks again for the great talk. It sounds like this type of model, like self-RAG, has longitudinal capabilities. So, for example, if our model was trained in, say, 2021, and then something happens in the future, then it can replace whatever fact is wrong with a new fact. I don't know whether you've done such types of experiments.
Yeah, we didn't try the experiments like experiments on like temporal changes, but I think it's yeah, it's highly doable. So what we can make sure is that we can simply like swap the timestamp with knowledge corpus. For example, like during our experiment, we use mostly like using like Wikipedia 2018, but we can also like use Wikipedia 2020. Actually, like we did in our experiment, like we used 2018 corpus for some data sets, but like we use 2020 corpus for like more recent data set. And what we have to do is like we simply needed to swap the knowledge corpus without changing the training data, because by doing that, instead of RAG training, basically like encourage the model to explicitly use information presented in the document. So the model learns to prioritize the retrieved document when it comes to generation. Well, like in case of normal RAG, still like we have seen like many cases where like the trained model prioritize its own parametric knowledge, and instead of using the retrieved document, it's still like generating the same answer based on the training data. So I think that's one advantage of our framework.
I actually had a question. So it seems like one assumption we're making is that generation can be conditioned on a single passage, which I think like, even though I think you showed that there's a beam search element to the segments, but individual candidate generation is being conditioned on only one passage, if I'm not wrong. And so I was just wondering if that is a problem, or is there ever a scenario where you would like to condition multiple?
Yeah, so in our case, yeah, we do retrieval multiple time during generation, so we can incorporate it. As a result, we can incorporate multiple documents. But yeah, I agree with you. Like we cannot use like two documents at the same time for like this one segment generation. But for that one, you can possibly like try to add like two documents at once for like each segment generation. There might be some cases where like this using two documents can be more helpful. For example, like you want to check like you want to compare two entity, like which one is younger, or like you can do like multiple reasoning as in like hot QA. And in that cases, possibly like the using multiple documents should be helpful. But in case of multi-hop reasoning, a model can retrieve multiple times. So the model can like retrieve one document for the first hop and then a second document for the second hop. So yeah, there's like we can explore a little bit more for those cases where like we want to use multiple documents at the same time.
That makes sense.
I think someone has a question and
Oh, hi. Yeah, I had a question. Akari, wonderful talk. I had a question on whether there's potential to further improve this by just doing a better job at predicting these like reflection and critique tokens, or is basically the model's already doing such a good job that there's not much more headroom?
So in terms of accuracy, it's depends on the aspect, but it's roughly like 80 to 90%. So if we want to make sure that like reflection tokens are more reliable, there are definitely more spaces for improvement. Like basically like 80% accuracy means like we make mistake on like 20% of cases. And one thing it might be useful is like simply like increasing the amount of the training data used during training time. And another thing which I believe important is like having a really clear definition or like better categorization, because the reason like we had more like diverse type of tokens, like 5 different tokens for like one aspect and so on, and I had a hard time to like make it work. So we had a bunch of discussion on like what kind of aspect we needed to have, and like what kind of like levels of like or the granularity of this like different reflection tokens. But I think the general framework can be easily applicable to like different type of aspect, fine-grained aspect, and we can like easily change the like level of like feedback. And so I believe that there are like many future spaces to explore.
Very cool. Yeah, thank you for the detailed answer.
I think we're at time. I think we can all thank the speaker again.
Yeah. Thank you so much for joining today. Okay, should I wrap up? Okay, thank you so much. Have a good day.